All right, so welcome back for part 2 of session 3.3. We're still working on the product rule, but we're going to take a look at how we can take that same product rule and we can extend it to cover products containing more than two factors. So suppose you had three functions, f, g, and h, and they were all differentiable. Then the derivative of f times g times h would just be, and I want you to take a look at the pattern here, f prime times gh plus g prime times fh plus h prime times fg. So I'm hoping that you see the pattern. It's one derivative, everything else stays the same. A different derivative, everything else stays the same. The third derivative, everything else stays the same. And if you had four functions all multiplied together, you could extend this out. And what you're going to end up with is just a whole bunch of things added together. And so if there are three functions, there are going to be three terms added together. Each has one derivative and two plain old functions in it. Okay? So when I look at what's happening with this one, I'm seeing three things being multiplied together. There's an x squared. Come on, erase. Sometimes, for whatever reason, the pen gets jammed up and just doesn't want to erase. There's an x squared. There is a sine x, and there is a cosine x. All right? So if we think of this one as the f, and this one as the g, and this one as the h, then f of x is x squared. F prime then would be 2x. G of x, sine x, g prime of x, here is sine is cosine. H of x is cosine x, then h prime of x would be negative sine of x, and then I have to string this whole thing together because our dy, our derivative of y with respect to x, dy dx, and that is going to become f prime times g times h plus f times g prime times h plus f times g times h prime. And then putting it all together, 2x times sine times cosine plus x squared times cosine times cosine plus, actually I'm going to recognize that there's going to be a negative in here. Okay? So plus, let's see, f was x squared, g was sine, and then h prime is a negative sine x. So then cleaning this up a little bit, we get 2x sine x cosine x plus x squared cosine squared minus x squared sine squared, and there's our dy dx. But, I'm wondering about something. Isn't 2 sine cosine like a double angle formula? And isn't cosine squared minus sine squared a double angle formula? I think they are. So I could probably simplify this further, but I'm not going to. But just so you know, it is trig, so there's probably a way to make this go further. You probably could do something here with a double angle formula on sine and turn this into like x sine 2x, because I believe that sine 2x is 2 sine x cosine x. And I think that cosine squared minus sine squared is some sort of double angle on cosine. So that could become like x squared cosine 2x, I think. I'd have to look up my trig sheet to know. Do I have the trig sheet still open? No, I got rid of it. Hold on. All right, so I open up the trig cheat sheet that I've got and look right there. Yep, I was right. Sine 2 sine cosine can be sine 2 angle, and cosine squared minus sine squared is cosine 2. So we could have taken this one and turned it into that. I'm not sure if that's an advantage or not, but it could have become x sine 2x plus x squared cosine 2x. I don't know. Some people would make the argument that this is better because it's only 2 terms versus 3 terms, but I don't see a need to do it. Okay? It was just talking to me, so I thought I'd look it up. All right. Moving right along, though, here's the big one, the quotient rule. And while the quotient rule is a very important rule in calculus, it is also, in my opinion, one of the ones that students make mistakes on the most. It is fairly involved, and because it is fairly involved, for whatever reason, whenever something is fairly involved, students struggle with it. All right, so let's take a look at what the quotient let me try that again. Let's take a look at what the quotient rule says. The quotient rule says that the quotient of 2 functions, f and g, 2 differentiable functions, is itself differentiable for all values of x for which g of x is unequal to 0. So we always put that little caveat in our definitions when we have fractions, that we say that the denominator can't be 0. Okay? But the actual derivative of f divided by g is complicated, and it's simply not easily memorized. So here we have it down here. Now this is the definition of the derivative in words. Here it is as a formula. Let's take a look at it. I'm going to call this top. I'm going to call this bottom. So the derivative of f divided by g is the bottom multiplied by the derivative of the top minus the top multiplied by the derivative of the bottom over the bottom squared. It is g times f prime minus f times g prime over g squared. Now, the same problem we run into with this one that we ran into with the f's and g's in the product rule. So you will sometimes see it written like this. U divided by v. Bottom, derivative top, minus top, derivative bottom, bottom squared. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the square of the denominator, v squared. Okay? There's a little sing-song you can do with this. Low d high minus high d low over the square of what's below. Now you might be going, what? All right. Instead of thinking of this as top and bottom, think of this as low. Think of this as high. And then it's low d high minus high d low over the square of what's below. And once you learn that, you could never forget the quotient rule. Low d high minus high d low over the square of what's below. vu prime minus uv prime over v squared. Or gf prime minus fg prime over g squared. Memorize it however you want to memorize it, but find a way to memorize it. Okay? This is the single most commonly missed derivative rule that we have, the quotient rule. Right? I cannot stress how important it is to memorize it. Okay? All right, so let's take a look at an example down here. We'll do this one on the left first. Okay? Now, first things first, I don't ever want to use the quotient rule unless I have to use the quotient rule. So anytime I see a quotient, I don't immediately just go, oh, it's a fraction, quotient rule, yay. I stop for a second and go, do I have to use the quotient rule? Is there any way for me to algebraically simplify this so that I won't have to use the quotient rule? And in this example here, our first example, there is no way to algebraically simplify this. I can't divide this out in any way. And since I can't algebraically simplify it, I'm going to have to use the quotient rule. Now for the first couple, I'm going to lay all the pieces and parts out, and then after that we'll try to jump right to the rule. All right, I'm going to use the u over v definition and say that the derivative with respect to x of u over v is v u prime minus u v prime over v squared. Right? My u is 5x minus 2, so then my u prime is 5. My v is x squared plus 1, so then my v prime is 2x. Okay? So then putting it all together, I'm going to get then that the derivative of y with respect to x is going to be v x squared plus 1 times u prime, 5, minus u, 5x minus 2, times v prime, 2x, all divided by v squared. Okay? Now here's where the second most common sets of mistakes are made. First most common mistake is just to screw up the formula, is to somehow mess this up. Maybe put a plus in the numerator, maybe switch the order of those two terms in the numerator, maybe forget the squared downstairs. That's the first most common mistake. The second most common mistake is this right here. Students will either forget those parentheses and forget to distribute the negative, or will in some other way screw up that distribution of the negative and all of that. Okay? The quotient rule is the one rule that has the most algebra after it. Okay? The third most common mistake is that students will see this, and they'll want to cancel those because they look like they're ready to be canceled, don't they? But you have to remember that that numerator is a binomial. There are two terms in that numerator. The first term is this, and the second term is that, and you can only factor and then cancel if x squared plus 1 is a term of both of those terms, is a factor of both of those terms in the numerator. Since it is not a factor of both terms in the numerator, then you can't cancel it. Okay? All right, so let's do some algebra, because I love me some algebra. So cleaning this thing up, dy dx. Right? Oh, in case you're wondering, yes, you have to clean this up. I can distribute this monomial here into that binomial in my numerator, so I'm going to get 5x squared plus 5. Distribute this monomial into that binomial, and don't forget that minus, so I got 10x squared, so that's going to be a negative 10x squared. I got a negative 4x, so that's going to be a positive 4x. And all divided by x squared plus 1 squared. Now, I know there's at least one person going, hey, you multiplied out the top. Why didn't you multiply out the bottom? The reason I multiplied out the top is because I have two terms up top, and I might be able to combine some like terms after I do that distribution. Downstairs, there's no good that's going to come from multiplying that out, because I'm hoping that somehow maybe when I clean up that numerator, it'll be factorable so I can cancel and simplify. But I don't see that happening here. All I see happening here is some like terms in that numerator that I can combine. Whoops, wrong one. To give me a negative 5x squared, a positive 4x, and a positive 5 over x squared plus 1 squared. And I think that that's just going to be the best that I can do with this thing. So negative 5x squared plus 4x plus 5 over x squared plus 1 squared. I'm not even going to attempt to factor this because it wouldn't do me any good. Even if it did factor, because it's a quadratic, it would factor into two linears, and the linears aren't going to cancel with that denominator, which is an irreducible quadratic. It's non-factorable, so I can't reduce it. I can't simplify it. And so it wouldn't do me any good to do it. So I hope that if you've learned nothing so far, you've learned that I'm a little bit lazy, and I don't want to do work for no good reason. So why would I factor something if there was nothing good that was going to come out of the factoring of it? All right. That's 15 minutes right there. We have time for one more, then we'll start a second video for the rest of this section. Okay. Again, I'm given an expression, a y equals a fraction, a rational function, and my job is to take a derivative. I have a numerator that I'm going to call u. That is going to be x squared plus x minus 2, and then u prime will be 2x plus 1. I have a denominator that I'm going to call v. It is x cubed plus 6, and then v prime will be 3x squared. Okay? And then my derivative, dy dx, is going to be the denominator, x cubed plus 6, times the derivative of the numerator, 2x plus 1, minus the numerator, x squared plus x minus 2, multiplied by the derivative of the denominator, 3x squared, all divided by the original denominator, squared. Okay? And this kind of gives you an idea of how ugly these things can get rather quickly. All right, I'm just going to dig right into this. I've got a binomial times a binomial here. I've had a trinomial times a monomial there. And I'm just going to start working this thing out. I'm going to erase this to get it out of the way because I don't think we need it anymore. Okay. First times first is going to give me 2x times x cubed, or 2x to the 4th. Outer is going to give me x cubed times 1, which will give me just plain old x cubed. Inner is 6 times 2x, which will just give us 12x. And last times last will give me a 6. And that's the first term. Now I have to do this second term. So I'll do this one in blue so it stands out. Now don't forget the negative, so everything we get, we have to change the sign. 3x squared times x squared is 3x to the 4th, so that'll be a negative 3x to the 4th. 3x squared times x is 3x cubed, so that'll be a negative 3x cubed. 3x squared times negative 2x is negative 6x squared, so that will be a positive 6x squared. And our denominator is just going to stay at x cubed plus 6 squared. Now I need to clean up that numerator. Okay? So my derivative, dy dx, is going to be, highest power I'm seeing across that numerator is a 4th degree, so 2x to the 4th, and there's only one. There's two terms. So I have 2x to the 4th, and I have negative 3x to the 4th, so that's going to be a negative x to the 4th. And then I got x cubes. I got a positive x cubed and negative 3x cubed for a negative 2x cubed. Then I got a positive 6x squared. And then I've got a positive 12x. And then I've got a positive 6. All divided by x cubed plus 6 squared. Okay. And I'm going to call that good because I don't think that this numerator is going to factor in any meaningful way. And since that numerator won't factor in a meaningful way, I'll just leave it just like that. All right, so we're at 19 minutes here, so we'll call this video, we'll come back, and it looks like we got 4 more examples of straightforward quotient rule problems to do. All right, I'll see you for part, what is that going to be, like part 3?